Energy can exist in numerous forms, such as thermal, mechanical, kinetic, potential, electric, magnetic, chemical, and nuclear, and their sum constitutes the total energy of the system. In thermodynamics, we are usually concerned with the change in the total energy of a system, and it is often helpful to consider the various forms of energy that make up the total energy in two groups, macroscopic and microscopic. The macroscopic forms of energy are those a system possesses as a whole with respect to its surroundings, such as kinetic and potential energies. The microscopic forms of energy, on the other hand, are those related to the molecular structure of a system and the degree of molecular activity, and they are independent of the surroundings. The sum of all microscopic forms of energy is called the internal energy of a system, U. In most cases, the magnetic, electric, and surface tension effects are insignificant, so we ignore them. We therefore express the total energy of a system as the sum of its kinetic, potential, and internal energies. We can obtain the total energy per unit mass by dividing through by the total mass of the system. And also, we can write the change in energy as such. Most closed systems remain stationary during a process, and thus experience no change in their kinetic and potential energies. And in cases such as these, the change in the total energy of a system is equal to the change in its internal energy. In SI units, we measure energy in joules or kilojoules. Energy can cross the boundary of a closed system in two forms, heat and work. We need to distinguish between these two forms of energy. Heat is defined as the form of energy that is transferred between two systems or between a system and its surroundings due to a temperature difference. Heat is also measured in the same unit as energy, joules or kilojoules. A process during which there is no heat transfer is called an adiabatic process. And there are two ways in which a process can occur without any heat transfer. One is if the system is well insulated so that no heat or a negligible amount of heat can pass through. The second is if both the system and the surroundings are at the same temperature, and so there is no temperature difference to drive heat transfer. An adiabatic process is not the same as an isothermal process. Even though heat is not transferred to the system, its temperature can still be changed by other means, like work. Work is the energy transfer associated with a force acting through a distance. It could be a rising piston or a rotating shaft, or it could exist in some other form. Work is measured in joules or kilojoules. The work done per unit time is called power, and it is measured in kilojoules per second or kilowatts. Heat and work are directional quantities, so to completely describe them, we have to specify the direction they're moving relative to the system. The general sign convention is as follows. For heat, heat flow into the system is considered positive, and heat flow out of the system is considered negative. And for work, work done on the system or work input is considered negative, and work done by the system or work output is considered positive. In some sign conventions, work input is considered to be positive and work output is considered to be negative, but we won't be using that convention. And the reason why we're following our convention is because most thermodynamic devices which operate on heat and work, like the steam engine, use heat energy to produce work. And so to measure the performance of these devices, we use the heat input and work output. This is why in our convention, heat input or work output are regarded as positive, while heat output or work input of our system are regarded as negative. Point functions, or state functions in thermodynamics, are functions that depend only on the state of the system and not on how the system reaches that state. Thermodynamic properties are point functions because they depend on and are used to describe the state of a system, regardless of the process through which that state is attained. For example, if we have a gas at an initial volume V, and it undergoes a process so that the same mass of gas now occupies a different volume, V2. We don't have to know what process it went through to determine V1 and V2. All we need to know are the initial and final states of the system. Point functions have exact differentials designated by the symbol d. So a small change in volume is represented by dV, and the total volume change during a process between state 1 and state 2 is represented by the integral, which gives us V2 minus V1, or delta V. Path functions, on the other hand, depend on the path followed during a process. Heat and work are path functions. Let's use the same example. Here, the volume of the gas has been reduced. There are many different processes that could give us this outcome. One possible way could be to remove heat from the system so that the gas cools and is compressed. Another means could be by mechanically compressing the gas, doing work on it. The first process involves heat flow from our system, while the second doesn't necessarily involve heat flow, but instead work input into our system. It would make no sense for us to say that the heat of the system changed from Q1 to Q2 in the first case, or from W1 to W2 in the second state. There is no such thing as Q1, Q2, W1, or W2. This is because systems do not possess heat or work. Both forms of energy are associated with processes. So instead, we say a certain amount of heat, Q12, was removed from the system in the process from state 1 to state 2. Or we say, for the second case, a certain amount of work, W12, was added to the system from state 1 to state 2. Path functions have inexact differentials designated by the symbol delta. So we use delta Q or delta W instead of dQ or dW. And the total work done during process 1 to 2, for example, is the integral of delta W from state 1 to state 2, which gives us W12, not W2 minus W1 or delta W. For a simple compressible system, we're going to consider a gas contained in a cylinder and piston. The pressure on this gas is maintained by weights placed on top the piston. Removing one of the small weights will cause the piston to move upwards a small distance dl. We can consider this a quasi-equilibrium process and calculate the amount of work done by the gas in moving the piston a distance dl. And this small amount of work is equal to the force exerted by the gas multiplied by the distance dl. The force here, F, is equal to the pressure of the gas multiplied by the cross-sectional area of the cylinder, A. So we can write delta W equals PAdl. The product, AdL, gives us the volume through which the gas has expanded. So finally, we can write our work done, delta W, equals PdV. This is the amount of work done by a compressible fluid when it expands through a small volume. If we have a continuous quasi-static process where the gas expands and pressure and volume are continuously changing, and we go from a state 1 to another state 2. Since we know the work done for a small expansion, dV, we can calculate the work done for the entire process from state 1 to state 2 by integrating this differential work between state 1 and state 2. So W12 equals the integral of PdV from state 1 to state 2 for a simple compressible system. This integral is the area under the PV diagram from state 1 to state 2. We assume a quasi-equilibrium process because With a quasi-equilibrium process, our curve proceeds smoothly from 1 to 2. If this wasn't a quasi-equilibrium process, our curve would look something like this. It's just made up of points because we're jumping from one equilibrium state to the other. In this case, integration wouldn't be possible, and we won't be able to calculate the work done for this. Also, it is possible to go from state 1 to state 2 along many different equilibrium paths. For these different processes, the work done will be different, even though we are moving between the same states. Again, this shows the difference between point functions like pressure and volume, which are independent of the process, and path functions like heat and work, which depend on the process. A cylinder containing a gas is fitted with a piston on which a number of small weights are placed. The initial pressure is 200 kilopascals, and the initial volume of the gas is 0.04 meters cubed. A burner is placed under the cylinder and the gas expands to a volume of 0.1 meters cubed. Calculate the work done if the expansion occurs 1. At a constant pressure, 2. At constant temperature, and 3. At a rate such that PV raised to the power of 1.3 is constant. So for the first process, a constant pressure process, we know that P1 equals 200 kilopascals, V1 is 0.04 meters cubed, and V2 is 0.1 meters cubed. We can calculate our work done using the relation W12 equals the integral of PdV from state 1 to state 2. So at constant pressure, P is constant, and we can factorize it from the integral. So we're left with the integral of dV from 1 to 2. And this gives us P into V2 minus V1. So substituting our known values into this, we get 12 kilojoules as our work done during this process. Now note that when doing calculations like this, you must make sure your units are consistent. So 1 Pascal is 1 Newton per meter square. And 1 Pascal times 1 meter cube is 1 Newton per meter square times 1 meter cube, which is 1 Newton meter or 1 joule. So 1 kilopascal times 1 meter cube is 1 kilojoule, and this is how we obtain our units. Next, to calculate our work done at constant temperature, we assume the gas is an ideal gas. So we use the ideal gas equation, PV equals RT. This uses specific volume, and for the actual volume, it is PV equals MRT. On the right-hand side, all the elements are constant: mass, the specific gas constant, and temperature. So PV is constant, and let's call this constant K. So we can say PV equals K, and P equals K divided by V. Putting this into our relation for work done, we have W12 equals the integral from state 1 to state 2 of K divided by V dV. And we can factorize K out of this integral since it's a constant. So we're left with the integral of 1 over V dV. And this gives us K times the natural logarithm of V2 divided by V1. Since PV equals K at all times, then P1 V1 also equals K. So the work done W12 equals P1 V1 times the natural logarithm of V2 divided by V1. And now we can substitute our values and obtain the work done, which gives us 7.33 kilojoules. Finally, if PV to the power of 1.3 is constant, let's call our constant G. So we can write P equals G divided by V to the power of 1.3, or GV to the power of minus 1.3. Now using this in our integral to calculate the work done, we have W12 equals the integral of GV to the power of minus 1.3 dV from state 1 to state 2. Evaluating this integral gives us G into V1 to the power of minus 0.3 minus V2 to the power of minus 0.3 divided by 0.3. Again, G equals PV to the power of 1.3. So That means G equals P1 V1 to the power of 1.3. And we can substitute that into our expression for the work done. So what we have is W12 equals P1 V1 to the power of 1.3 into V1 to the power of minus 0.3 minus V2 to the power of minus 0.3, all divided by 0.3. Substituting our known values and evaluating this, we get 6.41 kilojoules as our work done. Let's say we have a closed system. So, for this system, no mass flows in or out. The system can, however, exchange energy with its surroundings in terms of heat and work. Let's call the net heat flowing into the system Q net, and the net work output of the system W net. According to the law of conservation of energy, energy can neither be created nor destroyed. So we can write an equation to account for the energy flow. If an amount of heat, Q net, flows into the system, we have a positive change in energy. And if an amount of work, W net, is output from our system, we have a negative change in energy. So we can write Q net minus W net equals delta E, which is the change in our total energy. It's always important to remember our convention whenever we use this energy equation. For example, if 5 kilojoules of heat was supplied to our system and it did 2 kilojoules of work on the surroundings, the energy of the system would have increased by 3 kilojoules because according to our convention, Q in and W out are regarded as positive. If, however, 5 kilojoules of heat was added to the system and 2 kilojoules of work was done on our system, its energy would be increased by 7 kilojoules. The energy balance equation still remains valid because work input is regarded as negative according to our convention. Remember that we expressed the total energy of a system as the sum of the internal, potential, and kinetic energies. We can therefore write Q net minus W net equals the change in internal energy plus the change in potential energy plus the change in kinetic energy. And like before, most systems remain stationary, so a change in potential and kinetic energies can be neglected because they are equal to 0. Usually, we drop the net subscript and just write Q minus W equals delta U, where Q represents the net heat input into our system and W represents the net work output from our system. This is known as the energy equation for a control mass or closed system. If the system undergoes a process from state 1 to another state 2, we can usually write this as Q12 minus W12 equals delta U, or Q12 minus W12 equals U2 minus U1. We can also write it in differential form as delta Q minus delta W equals du. A special case for the energy equation we might consider is a control mass undergoing a constant pressure process. We assume that there are no changes in the kinetic energy and potential energy, and that the only work done during this process is associated with boundary movement. So Q12 minus W12 equals U2 minus U1. Since our work done is due to boundary movement, we can write W12 equals the integral of P dV from state 1 to state 2. We also assume that the pressure is constant, so we can evaluate this integral as P into V2 minus V1. So Q12 equals U2 minus U1 plus P into V2 minus V1. We can expand and rearrange this, so we get Q12 equals U2 plus P2V2 minus U1 plus P1V1. P is equal to P1 and P2 since it is constant. Remember, we defined enthalpy as the sum of the internal energy and product PV, H equals U plus PV. So H2 equals U2 plus P2 V2 and H1 equals U1 plus P1 V1. This means that the heat supplied in this process, Q12, equals H2 minus H1. And this means that the heat transfer in a constant pressure quasi-equilibrium process is equal to the change in enthalpy. We're going to need this relation when we discuss specific heats. Specific heat is defined as the amount of heat required per unit mass to raise the temperature of a substance by 1 degree. So C, which is our specific heat, is equal to the inverse of the mass multiplied by dq dt. dq dt is the heat added per temperature rise, and divide this by the total mass to obtain this value per unit mass. Specific heat is measured in kilojoules per kilogram Kelvin. For a closed system, we can write the energy equation in differential form as delta Q minus delta W equals du, or delta Q minus PdV equals du. At constant volume, the term dV is equal to 0, so we are left with delta Q equals du. Differentiating both sides with respect to temperature while the volume remains constant, we have dq dt on the left-hand side and the partial derivative of u with respect to t on the right-hand side. And we use the subscript v to indicate that we are taking the derivative while keeping the volume constant. Du dt is a partial derivative because the internal energy might also depend on other properties aside temperature. So the specific heat at constant volume, Cv, is given as 1 over m dq dt. And this equals 1 over m du dt, keeping volume constant. Now, because we're dividing by mass, the internal energy becomes the specific internal energy. For a closed system at constant pressure, remember we're able to show from the energy equation that the amount of heat added equals the change in enthalpy. In differential form, delta Q equals dH. So differentiating both sides by T, we have dq dt equals dH dt, and we use the subscript P to denote constant pressure. So the specific heat at constant pressure equals 1 over m times dq dt, which is equal to 1 over m dH dt. And again, because we're dividing by mass, this becomes the derivative of the specific enthalpy with respect to temperature, keeping pressure constant. We just obtained the specific heat of a substance at constant volume and constant pressure. But with ideal gases, we make certain assumptions which enable us to do more with these specific heats. The first assumption is that for an ideal gas, the specific internal energy depends solely on temperature. So instead of a partial derivative, we have a total derivative. Also, if the specific internal energy depends solely on temperature, then the specific enthalpy will also depend solely on temperature. And here's how. Remember that the enthalpy of a substance equals its internal energy plus the product of its pressure and volume. From our ideal gas equation, PV equals RT, we can replace the term PV in our equation for specific enthalpy with RT. So H equals U plus RT. If internal energy is a function of only temperature, then both terms that make up enthalpy are temperature dependent, since R is constant. And this makes the enthalpy solely dependent on temperature. So we can also write the specific heat at constant pressure as a total derivative. We can rewrite these relations as du equals Cv dt and dH equals Cp dt. And evaluating the integrals gives us u2 minus u1 equals the integral from state 1 to state 2 of Cv dt, and h2 minus h1 equals the integral of Cp dt from state 1 to state 2. The second assumption we make for ideal gases is that the specific heat for constant pressure and constant volume are constant values. So we can evaluate the integrals as u2 minus u1 equals Cv into T2 minus T1, and H2 minus H1 equals Cp into T2 minus T1. Finally, for an ideal gas, we can establish a relationship between the specific heat at constant volume and pressure and the gas constant. Again, using specific enthalpy, H equals U plus PV, or we can write H equals U plus RT. In differential form, we have dH equals du plus R dt. And we know dH equals Cp dt and du equals Cv dt. So we have Cp dt equals Cv dt plus R dt. Dividing through by dt, we're left with Cp equals Cv plus R, or Cp minus Cv equals R. And this is the relationship between the specific heat and the gas constant of an ideal gas. For an ideal gas, the ratio Cp divided by Cv is called the specific heat ratio. So let's have a quick summary of all the formulas we've learned in this video. First is the total energy content of a closed system. Next, we have the change in energy for a closed system. Then we obtained the boundary work for a simple compressible system at constant pressure undergoing a quasi-equilibrium process. The next thing we did was to establish our sign convention and derive the energy equation for a closed system. Then we applied the energy equation to a constant pressure process, showing that the net heat added is equal to the change in enthalpy. Finally, we derived the specific heat at constant volume and constant pressure for a pure substance, and we obtained specific heat relations for an ideal gas.